Okay, so let's do it for real. Okay, so sometimes you go to conferences like this one and you hear about like super interesting concepts like higher candidate types or things related to shapeless or monad transformers or the F monad. And you come out of the room and you think, wow, that looks super interesting, but how do I use this in my daily job? So the next day you're back at work and you have some microservice to code. You have some real job to be done. So how do you do this? And last year at RatMap Oslo, I gave an introduction to the F monad, explaining exactly what was the implementation, how it was using the type system to do all those things, and why it was interesting as an alternative to monad transformers. And after giving that talk, I realized, well, okay, maybe that's interesting, but that necessarily doesn't help people to see how they can use it at work. Is it something that you can use just in small parts of your code? Is it something that's going to completely structure your whole application and be kind of invasive everywhere? So for this talk, I thought it would be a good idea to give you a view of how we are concretely using it at Zalando. And what's practically, you could do many, many things, but I'm going to show you today exactly what we are doing with this F monad. So my company, Zalando, is a huge online shop for fashion, where you can buy trousers, t-shirts, shoes. Actually, it started with shoes. And, well, it's a big company. And as you can see, we have lots and lots of employees. And what's not shown on these numbers is the number of engineers we have in the company. More than 1,200. It's huge. And the reason is that not only we program the main app on the web that you can see, but we also do all of the software that goes in the warehouse, that goes for logistics. So that's lots and lots of software. And some of that software is actually pretty advanced in terms of optimization techniques, when you have to gather items in a warehouse and making sure that everything is collected in the optimal fashion. You need some really good software to be able to do that. And more precisely, inside Zalando, I'm part of a department called Brand Solutions, where we help other merchants sell their own goods on the platform. So they can even have their shop inside the shop. So for example, they can have their own web content with different pages that they can update themselves. They can follow all the statistics about how many people came to their specific shop inside the shop, bought something, and so on. So that's very helpful for them. And in the context of brand solution and in the context of trying to onboard as many merchants as possible on the platform, we had to develop this service called article service. It's actually a pretty small service. And its single purpose is just to help a merchant that has a given product, like a pair of shoes, and wants to sell it at a given price, to declare this. And the product is already created, so there's no lengthy creation process. We have all the product description already in the system, all the images already in the system, and so on. So it's just a declaration of, OK, I am merchant X. I can sell the shoes at this price. Please make them available on the platform so that people can buy it. So that's what this service, the article service, must be doing. And that thing is a microservice. So even if its primary function seems simple, it has to do all the things that microservices do. So it has to do authentication, it has to scale, it has to be resilient, it has, and so on and so forth. And we have to provide all of this. And OK, that seems classical. Another difficulty we have on top of that is that all the backend services we're talking to are actually moving, and moving quite fast. Because Zalando used to be a huge monolith, primarily a Postgres SQL database with lots of Java on top of it. And as the company grew, this could not be done anymore. So it has to be split into lots of services. So that's one of them, obviously. But you have other services, like services to describe the products, services to describe the merchants, the stocks, the prices, and so on. But this is still work in progress. Not everything is yet available. So it's pretty hard at first to say, OK, you have to implement a function, but on some sand that's quickly moving behind you. So how do you do that? Oh, And also, you need it quick, maybe not for tomorrow, maybe for yesterday. You absolutely need this service to onboard merchants now, because time to market is the key here. So what do you do in that situation? What kind of technology? What can you use? No, you panic. You're first to say, I don't know what to use. What can I use in that situation? It's too hard, too many constraints at the same time. So, well, actually, no. Maybe you don't panic. You take a step back and you look at some good old-fashioned technology. One thing that's not functional programming, that's just components. Okay, maybe we can help ourselves by structuring what we are doing by just using components. And maybe we can reread some of the classics about components. And that one is, I think, from the 70s. And this paper describes how to take a system and cut it into components. How do you define what are the right criteria to take for dividing the system into smaller pieces? And this article advocates that it's not so much what the components are doing that's important. It's more what they are hiding. What kind of change you want to isolate from the rest of the system. And this must be the primary criteria for defining a component. So yeah, I really encourage you to reread the old classics. And probably now you've heard microservice, components, and as you guess, it's done in Scala. So you might be wondering, okay, what do I use for dependency injection? So you want to build a service with lots of components. How are you going to wire them? What are your options? Some cake? Anyone? Okay, you can use one variant of the cake pattern to do that. Or you can use one of the libraries like MicWire or Juice. That's one possibility. Or you can say, oh, this is all too complex. Let's go back to Java and let's use Spring. I'm scared of the type-in dependency injection. So for this project, we tried another approach. Let's try something new, something radical, something that's never been done before. Let's try constructor injection. Because after all, what's wrong with constructor injection? So let's revisit that again. What's wrong with constructor injection? Good old constructor injection. And let's see how far we can go with just using case classes to model our configuration and to model our components. So let's say I have a case class to represent a thread pool. That means the number of threads I want to have in my application, right? That's a piece of configuration. So I know how to create one object of the type thread pool, and I can assemble this small piece of configuration into a larger one, which is the config object. That's for the whole application is going to have this and possibly some URLs or some, I don't know, the size of your caches and things like that. So you put all of this under another case class for the configuration. And if you want to create one for production, you just instantiate one, like this, for example. So how do you use then this piece of configuration? Let's say you have a component describing an HTTP client. Well, you just pass it as one parameter using constructor injection. And how do you build then an HTTP client component? Well, you need the application configuration. You extract the thread pool part of it, and then you know how to build your HTTP client, right? So what you have here is basically a function from application configuration to one of your components that's just going to extract the small part of configuration you need to build your component. So another way to see that is just to, am I coming back? Yeah, is to see this as some kind of reader. It's almost the same thing. A reader is a function going from something to something else. So here I'm just rewriting the same thing using the reader interface, if you want, right? And now we try to extend this idea. So those are the changes for my config. And the cool thing about having readers, sorry, like, where was I? Oop, that thing goes too fast. Wait a minute. Yeah, as implicits like that, is that we are going to be able to automate the construction of all those components and all the wiring of the components without any code by using shapeless. So we have a library called Grafter, which is implementing this idea, where basically because all those reader definitions are implicits, because shapeless is super good at taking any case class, decomposing it into the sub-parts, and then finding the requirements for the sub-parts and so on. So if you want to build an HTTP client from the config, Shapeless will, with this method called generic reader, will be able to recognize that to build the HTTP client, you need the thread pool configuration. And given that there's an implicit reader giving you that thread pool configuration from the larger config, it will be able to build a reader from config to HTTP client. So you have no code to write, basically. And we can even automate this and reduce the boilerplate even more by just having an annotation. So this one, reader of config, basically says, for my HTTP client, I know how to build an HTTP client from a configuration object. And this annotation will write the implicit reader definition for you. And then this scales. That means that if you have components containing other components by composition, like an HTTP server needing an HTTP client inside, well, you can also put the same annotation on top of the HTTP server, and it's going to recursively see if there's a way to build your HTTP client from the configuration. And if there's a way to do this, there will be a way to build your HTTP server from the configuration as well. So all the instances of reader are going to be found like that, and you don't have anything else to do. So how do you do this? How do you use this at the top level of your application? You just invoke the reader instance of your HTTP server, pass it your current configuration for production, for example. In that case, we just build the production configuration object from Scala code, but you could take this deserialize from a file, for example, and then you have your full object ready to be started. Okay, so this is a schematic of the whole microservice, if you want. So basically, it's an HTTP server because it's a REST microservice. It has a bunch of routes because we have different services inside this service. Those routes are going to extract all the HTTP parameters and do some authentication. And then they are going to pass the relevant information to some services, coding for the domain logic, if you want. And those services are going to use some clients for all the backend systems to do that, what they have to do, like set the stock of a given product. So this is one of the routes. So here we're using HTTP4S, which is yet another project from type level. And we're using a special dialect, if you want, of HTTP4S to describe the routes. So this one is called row. So this comes on top of HTTP4S. And row is actually super nice because because it's very well typed, we can generate all the Swagger files defining the API of our service from the code itself. So many people, they go from Swagger to code, and they generate some code from the Swagger file, but we do the opposite. We just generate the Swagger from the code, and then we just have to modify the code, and all our interface file will be defined for us. So that is super nice. So the only functionality of this component, which is the price route, is to extract the HTTP parameters and to pass it to the service. So at this stage, we see two components interacting together. We have the route and we have the price service. And if I want to test the route, I don't have to have a fully instantiated price service, right? I can just pass an interface. So now we can see another important part of this idea of using components is that not only you have implementations, but it's important to have interfaces because you can switch any kind of implementation you want. And you can define a price HTTP service and have a more concrete implementation like price HTTP4S service. And the implementation is not very different from what you've seen before. So price HTTP4S service is another component. And we use case classes again to model this. I mean, case classes is something that's easy and simple. The members are other components, that they are dependencies. And we extend price HTTP service to define its interface. And again, using a simple annotation, we will have all the boilerplate reader code that's necessary to instantiate the graph that's being created for us. So that's very easy. The only maybe slight difficulty in all of that is that the route is using the interface. It's not using the concrete implementation. So when you try to resolve all the types with the readers, you need to say for a given interface which implementation you are going to use. So that's, I would say that's an important point of that configuration style, is that for each interface, you need to specify at least one default implementation. And this is what we are doing here. We are saying for the price HTTP service, use that implementation, not another one. But it's not so much of a restriction, because in most of the software we are creating, there is one major instance, which is generally the one we use in production. That's the one we want by default. So it generally makes sense to have a default implementation for any kind of interface you produce. So that's one important thing. There's always one default implementation. So far we've been using simple things, right? Constructor injection, case classes, interfaces, and we're just using shapeless and some annotation to hide all the things which have been a bit cumbersome to build manually. So all of that is automated for us. But you might wonder, does this work if I put my HTTP client in a library? Because if you remember, the reader was working from config, which is an application-specific class, to a component. But if you want to put your HTTP client in a library, you don't know in which context it's going to be used. You don't know what's the config object that you will have at this stage. So does that break? I mean, and actually it doesn't, because you can still use implicits. And if you put your HTTP client in a library, you can say, you can still declare a reader for it by saying, okay, I know that I can create a reader from A to my HTTP client, provided that that A has itself a way to extract a thread pool. I don't really know yet what that A is going to be, but as long as you can give me an A like that, I know that I will be able to extract an HTTP client. And again, the implementation is just one word, is generic reader, and shapeless is going to do all the wiring for you. And in the client code, if you want to, the only thing that you have to provide is that A, is that instance showing that it is indeed possible to extract a thread pool from the configuration. And then implicit resolution, everything will be found again. So it also works with libraries, and it's really readers all the way down. Case classes, interfaces, and readers to wire everything up into one object graph representing your whole application. So constructor injection, I mean, it seems that it really works, right? Now let's see, do we have any other problems? Because creating the graph is pretty easy. And okay, does that help with unit testing? Well, yes, it helps with unit testing, because that's precisely one of the strengths of constructor injection, is that if you want to unit test a component, it's very easy to substitute the dependencies. You just put some mocks in there, and then it's very easy to just test the component you want to test. So it's like this Rubik's Cube. It's super easy. Even if you haven't done any Rubik's Cube before, I'm pretty sure you can do that one. That should be fine. What about integration testing? How does that work? That one might not be so easy. Because if you remember the graph that we have, with all those layers, when you do integration testing, you generally want to test all those components together. But you want to mock some of the components that are very low inside this graph, very at the deepest levels. And with normal, traditional constructor injection, it's very tedious, because you have to manually build all your graph again by injecting this dependency into that dependency into that dependency until you rebuild the full thing. So that's one of the reasons why people wanted to find something else that's just pure constructor injection, because that thing was made really, really hard. But maybe there's another way to see this problem, which is tree rewriting. Because after all this graph looks like a tree, right? And if you study compilers, you also have trees. You have ASTs. There are trees. There are nodes describing your program. And tree rewriting is a technique where to do your compilation or to do some optimizations on your code, you take an AST and you transform it into another AST that's optimized for something, for example, where you remove that code. So there are libraries for doing tree rewriting, and maybe that's what we need. And one of them in Scala is not very well known, but it's a great library. It's called Kiama, and it contains many, many things to work on languages. So it has a parser, pretty printer, and it has a very extensive tree rewriting library. So this is the one we used. And in Kiama, you define strategies where you say, OK, I'm going to walk down my tree, and I'm going to do some transformations on it. And so one of those strategies can be the replace strategy, where you say, OK, walk down the tree, and if you find a class that has this type, just replace it with a mock, because you want to do the testing. That's exactly what this strategy is doing. So you define a strategy, and then you rewrite the full tree with this rewrite method, and you try to apply the strategy everywhere. And this is effectively going to go through your whole application and just replace the nodes you want to replace. Then if you add a little bit more syntactic sugar on top of it, this is how you write your integration test. You say, OK, build me please a full HTTP server from the configuration, and that's easy because you have all the reader machinery to do that. And now please just replace that part that is hidden at the bottom of the tree. And that's just one line. And I think that's super important for testing, because if you want tests to happen on your project, they should be super easy to write. Otherwise, people, they tend not to write them, or they tend to write things that are hard to maintain and that do not want you to write more tests, right? So that's a technique to make it a lot easier to write the unit test, the integration test. OK. Another question happens when you use this kind of technique of instantiating trees, doing some tree rewriting, is how do you do singletons? Because the approach of using a reader for building a tree of components looks pretty nice at first. But this is the kind of tree you end up with. You end up with a tree which is really a tree. It's not a graph at all if you just use readers. So there are some nodes that are going to be kind of duplicated, and some nodes that actually should not be duplicated at all, like access to database or execution context, things that you don't want to see 100 times on your system just because there's a dependency to it. So you want to be able to go from this graph to actually that graph, where you can control which nodes are being made singletons and which are not being made singletons. So how do you do that? Well, same thing, free rewriting. So there's, again, a strategy where you walk down the tree and you say, OK, every time I see a node with that type, the first time I see it, I put it on the side. And every time I see, again, a node with the same type, I take my first instance. And that's the one I want. And the whole graph is going to be rebuilt like that. So then creating singletons in the whole tree, again, by here we just add a bit of syntactic sugar, is just saying, OK, now make singletons for all the major components, and they are going to be made into singletons in your graph. But you don't have to stop here. I mean, not everything has to be singleton. So if you want later on to say, oh, but in that context, I want that thread pool to be specific, it's also possible. So we have other strategies to say, OK, now you can modify. If you have a DoBe database, please set a specific thread pool for the database, because you don't want to use the thread pool for the HTTP server. So again, this is possible. So all in all, you can build pretty complicated graph, and you can also display them. So we have functionalities in the library to just output what the graph looks like, which is actually super important, because you are kind of dynamically modifying the state of the graph of your application. You really need to check that what you intended was what happened, right? So you can have a look at that and see if you have the right amount of singletons, and you can zoom on your graph and see that, OK, indeed, I have one DoBe database component here. Maybe I have different interfaces to access it, but I have just one, and that's really important. OK, one other aspect of this whole way of doing configuration is that you absolutely need to be lazy. Well, maybe it's like maybe it's also a lifestyle. I don't know. Just be lazy. It has some good benefits. But in this context, it has some really important properties that since we are doing tree rewriting, you don't want to start anything until the moment you want to start anything. So you don't want to start consuming resources as soon as you create a component. And I mean, I think one of the major issues in many Java libraries or Java frameworks or Java projects is that people instantiate things in the constructor and right away start consuming services, consuming events, accessing the database and whatever. And those components are super hard to reuse. So in that case, if you have an execution context, it's important to wrap it into cat.eval, for example, to make sure that thing does not start consuming resources right away. Because then you can do all the tree rewriting you want. It will be super fast. No resources will be consumed. And you can only start your application when you want, which is there. Starting application is, again, some tree rewriting where we just go through the tree and call the start interface. So if there are components that you want to start, they can extend the start interface, implement the start method, and just return a result. We go down the tree. We start each component from top to bottom. We collect all the results. So that's the strategy where we just start all the nodes. We collect all the results, and then we can say at the end what was the result of starting the application, because we have a list of every component that was started in order, and we can display that nicely. So that's cool. So in summary, we have come up for this project with a new style of doing configuration and dependency injection, based purely on some simple Scala concepts, and quite a bit of syntactic sugar on top of it. So you have the idea of just using case classes, no inheritance, just extending pure interfaces, so no mixing of traits where you have the trait order might be important, might be a problem, variable initialization might be a problem, no self-types, no heavy type machinery, just reader. We use tree rewriting to be able to write easily our integration tests, to have some control about what should be a singleton, what should not be a singleton. We stay lazy. That means we can rewrite as much as we want, and we have ways to start and actually also to stop the graph in a very disciplined order. So the strategy we have is very top to bottom, but you could imagine having more elaborate strategies, a more elaborate way of walking down the graph and do other things to start your application. That's good. But what about F? So some of you are probably have the question, oh, I want my money back. Wasn't it a talk about F in the first place? Yes, yes, absolutely. It's a talk about F. But I think, so F is an important part of the functional programming we do, obviously. But I think it's still important to emphasize that components are not dead. Even if you do functional programming, I do not believe that you should have unrestrained functions everywhere in your project. Some of them, they are closely related together. They should live together. And it's not a shame if they share some dependencies together. If they are not like just a beautiful snowflake that does not depend on anything, that declares all these dependencies by itself. Having some components to structure your program is super important. And I think that Grafter is another solution to be able to deal with how to build and manage components in our applications. So where does F go in that picture? So the problem with components is that you have interfaces, and those interfaces are describing methods, but if you just develop them as they come, they might not be super precise in what those methods are doing. So this method is taking some inputs, but what's the result of that method? So probably if this method is talking to another service, it's going to be asynchronous. So it will have some concurrency or asynchronous effect. Maybe this method can have errors. So it might have some kind of either return value. Maybe this thing is going to do some logging. How do you even know it's going to interact with the file system at some stage? So we use the fmonad to specify this. So we use the fmonad to say, okay, this method is basically returning a price, but is also doing a whole bunch of stuff that we are going to encode in a type parameter that we call R in that case. And so it's like a monad. It's like a general monad, like future. But in that case, we encode that it can have a lot more effects than just having the concurrency effect. And we are going to see an example what they have. So, this cannot be a full presentation on F, right? So I'm just trying to give you a hint of what the F monad is. If you have a computation like with some either values, so I'm pretty sure that you are used to have combining either values in a for comprehension, right? Where you say, okay, let's try to get the value A, then let's try to get the value B. Maybe getting A is going to fail, so in that case, I want to know it, so I will have a string describing the error. Or maybe B is going to fail. But if both of them are correct, I know I can combine them, I know I can add them. And then I can run this computation, check the result, and depending on if I have an error or not, I know what to do. One way of understanding what F does is to imagine that those either values are like requests to someone else, to an interpreter. So you say, a left request is a request for saying, hey, stop here. Stop all computations. Something went really, really wrong. Stop now. There's nothing else to do. You just have an error message. Or you have another request, right, which is, oh, I have a value. Everything's fine. Go on with your business. And the F monad is basically this. It's just storing those effects, left or right, having an interpreter deciding what to do with that effect. And if the interpreter is able to extract a value, like an A, then having a continuation, where you take that A, you produce another F value containing other effects that will be also interpreted by the interpreter, and so on and so forth. It's basically a list of continuations. But the trick is that not only you can have the either effect, but you can have all sorts of other effects. So this is what we are going to see now. So that's basically the same program where we write that we have an either effect, returning a string for error message, and this is how we run it. We call the run either interpreter. So out of the box in the library, you have lots of effects. So the eval effect for things that are delayed, the option effect for things which should stop, that may not yield a result, the either effect, we've seen that, the reader effect, state effect, list effect. There are, a bunch of them, but we are going to see how we are using them. So typically, one method of our components will be coded like this, like getPrice is returning a price with a bunch of effects. And in that case, we're using task, which is a concurrency effect, we're using logged, which is a logging effect. I'm going to explain, give more details about that. And we're using the flow ID effect. So now we are being very, very specific about what this method does. It does some very specific things. And when you call it, you have to say, oh, now I'm calling it with that precise stack of effects. That's how I want to call my method. And the type system will know and will force you to, if you really want to extract a value, will force you to call all the interpreters for each effect, like running the log, running a flow ID, running the async computation. So that's how you use this kind of thing. Now let's go back to the article service and talk about this flow ID effect, because that's one of the simple kind of effects you can have. So flow ID is basically a reader effect. So what is a flow ID? When you interact with a microservice at Zalando, you can be an external client, and you might have lots and lots of requests. So one way for you to track those requests is to provide us with your own request ID if you want. And actually, in the whole microservice, we don't really need this information. It generally has to go through and be passed to the backend so that eventually other systems can know what was the original request. So we just pass on this information. And basically, this is where a reader effect is useful, because you can say, OK, all of my computations are going to use this flow ID, but it's only at the bottom of my service where I need it that I can ask for it. OK, now I need to send that flow ID to another system. Please give it to me. And now I use the downstream systems and I'm like a ZOS client in that case, and I'm passing a flow ID to that system to communicate with a backend system. But otherwise, the only thing I see in my program is just computations that require a flow ID effect. I don't need to know more. So this is quite a simple one. And this is how I call this method eventually. Get the price, and then you need to run the reader and pass the flow ID from the client. And it's going to be threading all the computations until it's really needed. So another effect is the logging effect. So this is how we do logging. And if you think about what I said about either being requests, logging is the same. You are making logging requests to an interpreter. And you're just saying, can you please log an info or log an error or just log a warning? And then the interpreter will know what to do with this. And you need a bit of boilerplate code. So you have an ADT representing your effect. Then you need some methods like info to create F values that are using one of the methods from the library called send to send a given effect into a larger stack of effects. And then you need an interpreter. So this is one possibility for an interpreter for logging effects, which is going to say, OK, I have a computation with some logging effects. What do I do with them? So if I have an info of M, I can call a type-safe logger. And I know that the type-safe logger is going to write to disk some logging information. Oh, but that thing is a real effect. That thing is going to do some real thing. So maybe I should be more cautious, and I'm going to wrap this computation into an eval. So basically what this interpreter is doing is translating something that's really abstract, do an info logging, do an error logging, into a more concrete action. So it's translating logs into eval. And that's what we are doing here. And you will run the eval effect only at the end of the world in your main method. But then you can do more. I mean, that's just one choice of interpreter, but you can do other things which are also very interesting. For testing, for example, how is it infuriating that when you're trying to test something, you have a subclass coming from a library that's doing all sorts of logging in your console? And the only way to deactivate this is to change a configuration file somewhere, and maybe don't forget to put the previous configuration in your configuration. I mean, it's truly horrible. So with this, you can just have another interpreter that's going to say, oh, discard all the logs, just don't do anything with them. And then you will have no logs in your test. It's just another interpreter. But that's not the only one. You could also say, oh, actually, I want to test my logging, because logging is a super important part of what we are doing for operations. So I want to know if my logs are reproduced. I want to know if they contain the right type of information. So another kind of interpreter could be collect the logs. And it's actually very easy to do. You just interpret your effect, put all the logs in the list, and then you get them. So this is what we are doing for testing typically. OK, one other very cool thing about the F-monad is that it's not only a monad, but it's also a full applicative. So it might seem obscure to you, but the real effects of consequence of being an applicative is that you can run things concurrently. And for microservices, this is kind of important, because if you need to build an article containing some data and some price, you don't want to have to go to the two services in sequence, because you're just losing time. You know, you can just run them, and once you get the information, you put all of that together. So you can have methods like that, get brand, get price, use the applicative notation for combining computations in CATs. I don't know if you're familiar with that. And once you have the brand, once you have the price, you can create an article. And if your effect is a task effect, it will know how to run this concurrently. And you can even traverse. So if you have a full list of articles that you want to traverse concurrently, because, I mean, why wait that each article is being processed? You can just run all of this concurrently. You can also do the same. So we actually support lots of different async effects in the F library, just because there are lots of async effects in the world, I mean, in the Scala ecosystem. So the first effect we have in the Scala ecosystem is the future effect. And as you can see on this example, using the future effect with the future library, is not so much different than what you would have to do when you use normal futures in Scala, because with normal futures in Scala, you have to have this horrible execution context everywhere. And now you just have to say, well, I have a future effect in my computation that I will have to interpret later on. So we support future effects using Scala future as a backend, if you want. It's actually a bit more than this because it's called a time future effect, because you can also time out those effects, which can be, of course, useful for microservices. We support the Twitter effects, and then all the tasks. So the one from Scala Z, the one from Monix, the one from FS2, right? So yeah, I think we have other effects, but those are the main types of effects we support and we have on our configuration and on our components. And you might wonder, well, you don't have an effect. You could have used reader as an effect to grab your configuration, right? Why don't you do that? And actually, my experience is that I've seen many people use functional programming and hearing that what's the functional way of doing dependency injection is use the reader monad and put readers everywhere. And I think it's a waste of space. It makes things very complicated. And I much prefer the approach that we have with components, where we grab the configuration once and for all to build components with all the right dependencies, and then we have all the functions inside the component being completely free of this question, because they just have access to the configuration as part of the full component. Okay, so it's working quite well for us, but the road to this place was not so easy. So we made some mistakes. One of them, which I see very often, is to define the stack you're going to use to create those F values too soon. The beauty of the F monad is that it's an open stack of effects. So you just say what you require, but you could have more. You could have people invoking your methods and in a context that has more effects just than the ones you need. If you declare a method like that, get price, it will be fixed with those 3 effects. And it will be actually a bit difficult for other methods to call this one. So I really encourage you to leave things open and use this kind of notation that's just saying, my R is a stack of effects. I don't know what's inside, but at least I want to have this. And this will lead to a nice composition of effects. And all those methods are going to be nicely composed. Another issue we had was, how do you deal with errors? Because now you have the F monad, you have at least 3 possibilities. So one of them is the classical one. Just return a value that encodes the possibility of an error using either. That's very classical. Another one is to have more complex data types, like get price results will be an ADT, where you have a base result that's OK, and some error cases with a list of messages, for example, things like that. Or you could use also the throwable either effect, which is another way to encode the possibility of having errors in your program. And it turned out that when we started with all of this, we had 3 of them. We were using 1 style per layer in our application, and it was not necessarily easy to compose between all of them. It was a bit difficult. So my recommendation is don't go crazy on your error types, because you will have to do all sorts of conversions between one and another. So try to say simple, and use the following trick, which I might not have lots of time to explain, which is that if you use a stack of effects, you can locally, in the scope of a method, say, oh, just for now, I'm just using one more effect, which is the either effect. So if you want to have, let's say, 2 methods which are returning either objects, you can say, oh, with the collapse method is going to help you transforming an f of either into just an f of a. And it's going to put the either concern on the side. So that you can chain all sorts of computation returning either values, not worry about the either values for now, and you will just have to worry about them at the end when you go run either. This is all explained in the user guide, so you can take the time, go home, go on the website, immerse, play with it, because that's a very useful trick. Another error that we did, which I think was inspired by lots of tutorials out there on the free monad, was to make everything a DSL. Like, no, that was not a good idea. It was to think that maybe just getting a price should be its own effect. Price requests should be its own effect. And so we tried that. And then all components became very, very complex because they had to be interpreters. And they had to have this awkward type signature because this type signature for interpreters is a bit involved. And then we were realizing that we were creating effects, getting back an F value, and then interpreting them, and then getting back the result. And it was almost always the same. So eventually we decided to go for something, and then all these crazy DSL effects were bubbling up the top of the application. So we decided to do things that were a lot more simple and use mostly the effects I've shown you, like task, logged, flow ID, eval, reader, and some, or state. I mean, things that were very simple as our main effects. And we don't have any DSL effect like get the price or Hadoop effect or things like that. And then the signature of our components are pretty simple. They're just normal Scala methods. Okay. I'm going to skip that one or maybe go really quick and just arrive to the conclusion of that one is when you're modeling a component, should it be a component or an effect? And like if you want to get the current time, should you have a component giving you the current time that you use everywhere? Or should you have a time effect that you can interpret later on to get the time? And it's not an easy decision. And the criteria to decide about what you should do is about what kind of flexibility you want to give to the users of that time component. If you encode this as an effect, you give an opportunity to the clients of those computations to interpret time differently. It's exactly the thing that we did with logging. When we declare the logging effects on our components, we tell the clients, I've been doing some logging, but maybe you want to do something different about those logs than me. And you have this flexibility to do so. There's also a cost associated to this flexibility. The cost is that you have to provide an interpreter, you have to know things about logging. And the alternative would have been, okay, I'm doing all the logging myself, and you have no way to remove it. So there's this balance between the more flexibility you want to give, but also more responsibility you are going to give to people because they will have to interpret your effects at the end. Okay, let's do a quick recap. I think that components are still super useful. It's like technology from the 70s, but it's really simple to use in Scala. Case classes, interfaces, and a bit of shapeless and annotations on top of that can really, and tree rewriting can help you go a long way. And then there's a way to specify really precisely what those components are doing using effects. And that gives you lots of flexibility, lots of precision, and lots of composition. So yeah, that's it. Now it's your turn.